Let's answer the questions from the Arenes Quiz. Ethyl benzene is an example of an aromatic hydrocarbon. Write a balanced equation for the oxidation of ethyl benzene using hot acidified KMnO4. So this is how you balance it. So ethyl benzene will be oxidized to benzoic acid. This carbon here will be oxidized to carbon dioxide. And the rest of the hydrogen will be oxidized to water. So let's balance the hydrogen. Since there are 5 hydrogen on the left hand side, there's 1 hydrogen over here, so you need to balance by putting 2 here. So now let's balance the oxygen. So since there are 1 2 3 4 5 6, so you need to balance by writing 6 O. Alright, so this is the balance equation for the oxidation of ethyl benzene. Okay, let's look at the next question. Okay, given that the percentage yield is 80%, what's the mass of the organic product formed when 1 gram of ethyl benzene undergoes the oxidation reaction? So let's first calculate the number moles of ethyl benzene. So 1 divided by the relative molecular mass of ethyl benzene, which is 106. This will give you a value of 0.00943 moles. So since the number moles of ethyl benzene and the product is in a ratio of 1:1, as you can see up here, 1:1. So the number moles of product is equals to 0.00943 multiplied by the relative molecular mass of benzoic acid, which is 122 times 0.8. So that gives it 0.921 grams. Ethyl benzene prepared by the reaction of benzene with chloroethane. So this reaction is a Friedel-Crafts alkylation reaction. Explain why the reaction above would not occur in the absence of aluminum chloride. So let's look at what's the role of aluminum chloride. Aluminum chloride acts as a catalyst to form CH3CH2+, which is actually a strong electrophile. So we are looking at some of the keywords. So acts as a catalyst, and it forms CH3CH2+, which is a strong electrophile. So a stronger electrophile is needed in this case because of benzene, which is actually very stable. Okay, it's resonance stabilized. So you need to have a very strong electrophile to attack the benzene ring. Okay, describe the mechanism of this reaction. So the mechanism of this reaction is known as electrophilic addition. So the first step is the generation of the electrophile. So you are generating the electrophile, which is over here. So the second step is the attack of the electrophile on the benzene ring, and this is how we show the electrons moving from the pi electron cloud of the benzene ring to the carbon. Okay, this is how you draw it. So you form the intermediate carbocation ion, or the carbocation intermediate. So the third step is the loss of the proton. Draw the arrow coming from the CH bond back into the benzene ring. And with this loss of this proton, H+, which will combine with AlCl4-, it will regenerate the catalyst. So this is a catalyst that's regenerated. And resulting in the formation of ethyl benzene. Okay, let's look at the next question. Deuterium is a heavy isotope of hydrogen. When deuteriobenzene undergoes Friedel-Crafts alkylation, a mixture containing ethyl benzene and 3-ethyl deuteriobenzene are produced. and they say the carbon deuterium bond is broken as often as the carbon hydrogen bond. So what it means is this carbon deuterium bond can be broken as easily as any of the carbon hydrogen bond. All right. So why is the molar ratio of these two 1:2? This is actually 1:2. 1:2. Right. So that's a question. So let's see why that's so. In order to form ethyl benzene, this CD bond must be broken. So since the carbon deuterium bond is broken as often as the carbon hydrogen bond, so the probability of forming ethyl benzene must be 1/6. What's the probability of forming 3-ethyl deuterobenzene? In order to form 3-ethyl deuterobenzene, this hydrogen bond could be broken to give this, or you could actually break this hydrogen bond and you still get back the same compound. So the probability of forming 3-ethyl deuterobenzene is actually 2/6. So that will give you a ratio of 1:2. Right? So they say that the ethyl cation can substitute the hydrogen atom from two possible identical locations. So these are the two possible identical locations. Right? Okay. Next, the CD bond actually has a higher bond strength than the CH bond, yet CD C6D6 is alkylated at the same rate as the normal benzene C6H6. Since the question says that they have the same rate, and yet CD and CH bond have different bond energy, what it really means is the rate determining step, which is the slow step, will not involve the breaking of the CD bond. So in this case, this has to be the slow step and this has to be the fast step, because in step 3 it involves breaking of the CH bond. So this cannot be the slow step. And in this case, step 2 doesn't involve breaking any CD bond, but step 3 involves breaking of the CD bond. So this has to be the fast step and this has to be the slow step. So the slow step does not involve breaking of the CD or CH bond. Let's look at question D. You're supposed to distinguish the following compounds by carrying out only 2 simple chemical tests. So you have cyclohexene, benzene, and methylbenzene. So let's look at the first answer. If you add liquid bromine, let's see what happens, but in the absence of light. So reddish brown bromine is decolorized for cyclohexene because of the presence of the alkene. Okay, for benzene, it doesn't undergo decolorization because of the absence of a halogen carrier like aluminum bromide. So there's no electrophilic substitution that can take place. So there's no decolorization. So similarly for this, there's no electrophilic substitution for the benzene ring because of the absence of a halogen carrier or catalyst like aluminum bromide. And the methyl group can also not react because of the absence of UV light. So free radical substitution cannot take place. Let's look at the second one. Okay, let's look at adding liquid bromine under UV light. So since there's a liquid bromine, the same thing, electrophilic addition can take place for cycloalkene, and reddish brown bromine is decolorized. Absence of catalyst, no decolorization. In this case, since there's UV light, the methyl group can undergo free radical substitution. So reddish brown bromine is decolorized. What about adding KMnO4? Adding KMnO4 can cause oxidative cleavage of the alkene, so purple KMnO4 is decolorized. Benzene ring cannot be oxidized, so no decolorization. the side chain of the benzene ring can be oxidized to benzoic acid. So purple camphor is decolorized, and benzoic acid form is actually the white precipitate. Let's look at the last possibility. Concentrated nitric acid, concentrated sulfuric acid heat. There's no reaction with the alkene. So this will cause electrophilic substitution to take place for benzene. So there's a yellow oil of nitrobenzene. So this is your product. Alright. Same goes for methyl-benzene. You probably could get a product like this, since CH3 is 2,4 directing, right? So you still get a yellow oil. So the nitrobenzene is actually the yellow oil. So write an equation for the reaction that represents the enthalpy change for hydrogenation of cyclohexene. So this is just cyclohexene reacting with hydrogen to form cyclohexane, and the enthalpy change here is actually 120 kilojoules per mole. All right. Okay. Let's look at E part 2. Naphthalene is another example of aromatic hydrocarbon. So naphthalene undergo hydrogenation to form decathlene, and they say the enthalpy change of hydrogenation of naphthalene is minus 345. So this is minus 345 kilojoules per mole. The resonance energy of naphthalene can be defined as the energy difference between the actual structure of naphthalene and the hypothetical polyalkene structure. And then you're supposed to calculate the resonance energy of naphthalene by drawing a suitable energy level diagram, incorporating the relevant data. So let's look at answer key. So to hydrogenate one alkene is minus 120. So in this case, since you are hydrogenating 5 double bonds, so it will be minus 120 times 5. All right. And the hydrogenation of naphthalene was given to be minus 345. So the resonance energy is the energy difference between the actual structure of naphthalene and the theoretical polyalkene structure over here. So this is the resonance energy, right? You take the difference, it'll be minus 255. So explain the significance of the resonance energy. So naphthalene is actually more stable because it has all these p orbitals, all right, and the pi electrons in these p orbitals can actually delocalize, right? So because of the delocalization of the pi electrons throughout the ring, it makes naphthalene having a more stable structure, and we say naphthalene is actually resonance stabilized. So you can see from the diagram, naphthalene actually has a lower energy than the theoretical structure. Okay, let's now do part 4. They say calculate the approximate value for the enthalpy change of hydrogenation of the actual structure of anthracene. So let's put in the value. Let's do part 4. So we are actually trying to find out the enthalpy of hydrogenation of the actual structure. So firstly, this is the enthalpy of hydrogenation of the theoretical structure. This is the enthalpy of hydrogenation of the actual structure. So that's what we're trying to find out. And this is of course the resonance energy. So we can actually create an equation like this. Enthalpy of hydrogenation of theoretical equals to hydrogenation of actual plus the resonance energy. So just do a bit of rearrangement, we will get this equation. Enthalpy hydrogenation of actual structure equals to hydrogenation of theoretical minus resonance energy. So let's put in the value now. So in this case, we're actually hydrogenating 7 double bonds. 1 2 3 4 5 6 7. So the value will be 7 multiplied by minus 120. Alright, and for the resonance energy, how do we know? So this, look at the right hand side. When it involves 2 benzene ring, the value is minus 255. So in this case, since you're involving the formation of 3 benzene ring, so the resonance energy can be taken to be minus 255 times 3 divided by 2. So we can actually place 3 over 2 over here. And this will give you a value of minus 457.5 kilojoules per mole. There's actually another way of doing it. If you consider this on the right hand side, you're actually hydrogenating 5 CC double bonds, but on this side you're actually hydrogenating 7 double bonds. So instead of minus 255, you can calculate it as minus 255 multiplied by 7 divided by 5. So because now there are 7 CC double bonds compared to originally where there were only 5 CC double bonds. So in this case, you can place the value here, 75, and this will give you an answer of minus 483 kilojoules per mole.